Now for some derivatives using the product rule. Let's see what this one tells us. The product rule, if we have the product of two differentiable functions, well, f and g, so differentiable means we can take the derivative of f and the derivative of g. So if we took the product f times g, that is also differentiable. Now this right here is some notation, and the rest of it just tells you exactly how to do it. It's saying it's the first function times the derivative of the second, and then you add to that the second function times the derivative of the first one. There's many ways of learning this. This is how your textbook has it. I'm not sure how Mrs. Babcock and Mrs. Ware do it, but I want to show you some variations. First off, you're going to see this written quite often without the x variable, and hold on, I got to get it darker. So if it's not written with the variable x, you're going to see it written as f times g prime plus g times f prime. Okay, it's just showing you the functions without the independent variable. For other notation, it means the exact same thing. This right here can also be written as the product of f and g, find the derivative of it. Well, the derivative of that product, the way I learned it in school, and I've been doing it like this ever since, is you take the derivative of the first, you leave the second, plus you leave the first, and you take the derivative of the second function. Now, regardless of how you memorize it, it's the same thing, because I'm multiplying the product of this thing right here, and I'm multiplying the product of this thing right here, and since addition is commutative, you get the exact same answer all the time. The only reason I write it like this is because this helped me back in high school learn what's coming up next, which is the quotient rule. I'm not going to get into it, but that looks like the numerator of the quotient rule, so that's the only reason I write it like that. I think it helps you later on. But I also know that Delta Math writes it differently. Delta Math, they are going to write the product rule in this format. They're going to say, what did I see there? It's going to be f prime times g plus g prime times f. And simply because multiplication is commutative, it really doesn't make a difference which one comes first or second. So they're all mathematically equivalent. Now with that said, your teacher may do it in one of these formats. I'm going to tell you right now, I'm going to do it the way I've always been doing it. So let's move on. Now for the product rule. Say we have a function y, and the y consists of the product of two different things. These things are just expressions, but onto themselves they are functions, right? This is a function, this is a function. So I could think of this one right here as being my f, and this one right here as being my g. Sorry, that's a g. Well, if you follow the rules up here, the derivative of y, which could be written as y prime or dy dx, it states that I'm going to take the derivative of the first one. The derivative of the first one becomes 3. It says I leave the g. That would be x plus 4. Plus, now it tells me I leave my f, which was 3x minus 2. And now it's time to take the derivative of g. Well, that just becomes 1. And this right here is the product rule. We can clean it up a little bit. 3x plus 12. And, well, 1 times anything is itself. This is a simple combination. Let's add up our like terms. We have a 6x plus 10. Now, I just want to tell you right now, most of you be able to figure that out, but Delta Math just wants you to practice the product rule. They don't care if you leave it in that format. Now, this one's pretty straightforward, but we're going to do a next example where it gets a little sloppier, and you may not want to multiply these out. But Delta Math will accept any format, even if you do it in the other formats I showed you on the last slide. Now, some of you might be looking at that and saying, can I do this? Can I just multiply it all out? Well, if you did that, let's see what happens. You get 3x squared. That's 3x squared. This is a 12x. And then I get a negative 2x and a negative 8. And we didn't take the derivative. We're just cleaning up our y equals. That's a 3x squared plus 10x minus 8. And if you want to take the derivative at this point, hey, look at that. You get the same answer, and it seems like it's less work. Well, for this type of problem with two binomials, it is. Let's do an example now where you may prefer to use the product rule over just multiplying it out. Now for this one in yellow. Now this one, yeah, you could go right ahead and multiply this all out, but it almost seems like more work than it's worth. I prefer the product rule without a doubt on this one, so let's see how this would work out. We are finding the derivative of y, which can be written as y prime or dy dx. And if I'm going to treat this one as my f function and this one as my g function, let's continue. You take the derivative of f. Constants become 0. This becomes negative 4, x to the negative 3. Don't forget, when you subtract 1, that's a negative 3. All right, so we took the derivative of the first one. Now we're going to leave the second one. Plus, now we leave the first. And we take the derivative of the second. I'll do the derivative of the second in this color just to change it up. And what are we going to get there? We're going to get a negative 7. The negative 1 is 0. And this becomes negative 8, x to the negative 2. Again, when you subtract 1, you get negative 2. And this right here is what I mean. The Delta Math is going to accept this as the correct answer. They just want you to practice the product rule, and you just did. This is the derivative of the first, you left the second. This was the first, you took the derivative of the second. If you'd like to multiply that out, be my guest. You don't need to, no need to. Now the product rule gives us another plan of attack for evaluating derivatives, and the reason we want to know derivatives is, well, that's going to find instantaneous rates of change for us. So say we were asked to find the instantaneous rate of change of our function at a certain point, in this case when x is negative 1. Well, don't forget the instantaneous rate of change is your derivative. So we're asked to find the derivative, but we're asked to find, here, let me write it over here. We're asked to find the derivative when x is negative 1. That's what this is asking us, okay? We have to find what that equals. Let's continue. So the derivative of this, well, this would be the first piece. So if I follow that pattern, I'm going to take the derivative of the first, which is positive 2, x to the negative 3. The 3 goes away. I leave my second polynomial. And then I'm going to add to that, I leave my first polynomial. And I multiplied it to that, the derivative of my second one. Negative 1, x to the negative 2, and constants become 0. All right, well, that right there is a derivative, and it's pretty nasty looking. But what if we were to evaluate this derivative when x is negative 1? Well, first, before I even think about plugging in a 1 in there, I am going to write these as fractions, because even though you don't like fractions, it's easier to see what's going on here. This term right here is the same as 2 over x to the third. This is negative 2x plus 1 over x minus 4. This one is negative 1 over x squared plus 3, negative 2, negative 1 over x squared. Now it will be easier to see what this is evaluated at negative 1. I think I said evaluated at 1 earlier, but I meant negative 1. But regardless, it's easier to get it into fractions first. So wherever you see your x is where you plug in a negative 1. So just give me a moment. And finally, negative 1 squared. Let's see what we get here. So let me change the color here. We have negative 1 times negative 1 times negative 1. That's a negative 1, which means that simplifies to negative 2. This right here is a positive 2. That's a minus 1. That's a minus 4. Plus, negative 1 times negative 1 is positive 1, but there's a negative there, so it's negative 1. Negative 2 minus negative times negative is a positive 1, but there's a negative. It's negative 1 over 1. This simplifies to be negative 2. Let's see, that's 1. And 1 minus 4 is negative 3. And over here we get plus, and that is 3 minus 1 is 2. And this one over here is a negative 3. What does this equal? That's a positive 6, and that's a negative 6. So ironically, the instantaneous rate of change for this function at x equals negative 1 is 0.